So here's a little practice using a classic roller coaster design, and I threw in a little curveball at the end. It's actually going to be stopped. This ball is going to be stopped by a spring, and we can assume it locks into place at the end. So I've defined the total energy of the system by releasing it from rest at this point. I told you the mass, 3 kilograms. We have the height. This is h, or if you like, delta h. It's the potential change in height that it can go through. This is our ground level. I'm just going to say h equals 0. And we can forget about the whole rest of the coaster for a second. We're going to map out beginning, middle, and end, A, B, and C. But let's just focus on the first part, defining the total energy of the system. Because if we can find this total energy, then we can actually use it all the way throughout. We're assuming no loss due to friction. There's no water hazard or anything down the bottom here to slow us down. Assuming no air resistance. We're going to keep it very, very simple in terms of energy accounting. And the elastic potential energy actually doesn't come into play until the end. So this is great. Kinetic energy at the top. Kinetic energy, energy of motion. There's no motion. No motion, no kinetic energy. If you were to plug it into the kinetic energy is 1/2 mv squared, you know the mass, 1/2 is just 0.5, but the speed's still 0. So it ends up that kinetic energy at point A is 0. So that means in this case, all of the energy is just stored gravitational potential energy. How's that defined? GPE. Let's see. GPE is mass times gravity times height, or you can say delta, or change in height if you'd like. It's harder to type that, so I'll just assume that. So what is that height? 7 meters. What's the mass? 3 kilograms. We know the gravity in this case, 9.8 meters per second squared. Let's see, 3 units are okay. 3 kilograms times 9.8 meters per second squared. Remember that squared is just part of the unit. Does not affect the number at all. A lot of people get mistaken on that. And the height through which it could fall is 7 meters. Handy dandy calculator. 3 times 9.8 times 7. 205.8 joules. Remember, if I go too fast for you on this, it's a video. Go back. Slow it down. So 205.8 joules. Is that correct? Let's go back through. 3 times 9.8 times 7. Yeah, 205.8 joules. Good. So that defines the total energy of the system. I'm just going to, for simplicity's sake, round it to 206. So the total energy of the system, it's all these energies added together, it's 206 joules. Now watch. Total energy is boring. I'm not even thinking about what these systems look like on the end, but I know the total energy has to stay the same. 206 joules. Total energy is boring. Total energy does not change. So this speeds up, speeds up, speeds up because it's under the acceleration due to gravity. It's falling down the ramp, and we reach a point. It's going nice and fast, and then it comes up to a little loop. It's still going pretty fast. Still going pretty fast. It's only up 2 meters at its best. Assume that the diameter of the ball doesn't matter, by the way, so it's pretty much right up here. And from this 2-meter height, we can then again define the gravitational potential energy. You don't know what the kinetic energy is. There's a shortcut that I've shown you before which you could use to find that. But let's just go ahead and keep it basic. What is the gravitational potential energy here? Well, In this case, GPE is, again, mass times gravity times height. It's that height through which it could have fallen, which it could still fall. So it's 3 times 9.8 times now 2. It's not 5. It's not that difference in height from top to bottom. We could use that to find the kinetic energy if we wanted. But all we're trying to find is how much of this energy is still now stored as height, as energy of position, or gravitational potential energy. Handy dandy calculator. 3 kilogram mass times gravitational acceleration times now just 2. So it's a fraction of what was there before, which makes sense. This ball's moving. A lot of its energy is in kinetic energy. So 58.8, I'll write that down for you. 58.8 joules. And that's stored as gravitational potential energy right here. And just again, for simplicity's sake, we'll round it to 59. A little rounding going on, that's all right. What's left? Total energy is boring. Here's the total amount I have. I have $206 of energy. I've given gravitational potential energy $59 of it. What is left in my wallet? Oh, well, I can do that. $206 or 206 joules of energy minus $59 or 59 joules of energy. I still have 147 bucks in my wallet. So to follow this, there's 147 joules of energy that's now in the form of kinetic energy. It's moving this ball along. So as it continues on, now it's all back to kinetic energy. Actually, at this point, it's all 206 joules of kinetic energy because it can't go any further. And then it goes up a little bit, just 1.1 meters, right before it's about ready to come to a stop. It's going very fast still at this point. And it's exactly the same process. Could we find the kinetic energy first? Sure we could. But let's just stick with the same process. Find the gravitational potential energy. Realize that total energy is boring. Subtract the two. Whatever's left has to be kinetic energy. That's that energy accounting. Gravitational potential energy is, again, mass times gravity times that height through which it could fall. 3 times 9.8 meters per second squared times now just 1.1 meters. Handy dandy calculator. 3 times 9.8 times 1.1. 32.34. I'll write that down. 32.34 joules of energy is now stored as gravitational potential energy. So roughly 32. It's less than what it was at the top of the loop-de-loop because we're further down. Literally, less energy is stored as energy of height or energy of position, this gravitational potential energy. So most of the total energy is just going into keeping this thing moving. I have 206 joules of energy in my wallet. I subtract out 32 joules of energy, which I've stored as height, gravitational potential energy, really. My energy wallet has 174 joules. All is kinetic energy. So now I ask myself, what can I do with this? I want to bring this ride to a stop. Please, just end the ride. Well, I'm not going to just want to run into a wall. I want to bring this thing to a stop in a long enough period of time where the ball is not injured or the people riding on this ride are not injured. So in this case, I've just modeled it as a spring. So we're going to actually need to figure out these questions. I've given you the elastic constant for this spring. I said it's 200 newtons per meter. I just chose that value for this. It's like a lab scale experience. And we need to figure out how far this spring is going to compress, how much work was done on the spring, what average stopping force is required, because if the stopping force is too high, then it could break the materials or it could hurt the passengers. The maximum stopping force, again, we'll just find that theoretically. And then I want to give you a little bit extra practice with area beneath the curve. I'll show you how that works. So let's look at this question B first, work done on a spring. If we take that total energy, it was 206 joules, but 32 joules of it was stored at this point as gravitational potential energy. That doesn't change because this spring stays at that height of 1.1 meters. So we're not letting this ball move up or down any. So really the energy that we have to work with now is 174 joules. So 174 joules of kinetic energy at this point. Once this spring is fully compressed, the elastic potential energy should be, assuming no losses, should be 174 joules. How can I say that with confidence? Again, energy conservation, it holds true. If I had 174 joules of usable energy here, once I let this ball do work on the spring, or the spring working against the ball, whichever way you want your perspective to be, I'm storing energy in that spring, elastic potential energy. And I'm not losing anything to thermal energy. That's my idea. I'm looking at the ideal world. It must all be stored as elastic potential energy. It can't be stored anywhere else. So that is also the work done on the spring. That's that work energy theorem that we've talked about before. The idea that work and changes in energy are the same thing. They're equivalent to each other. So if we know that the elastic potential energy is, how much was it? 170 joules? Am I correct on that? 174 joules? If we know that that's the case, then we can actually also use the elastic potential energy equation, 1/2 times the elastic constant times the amount that this compresses squared, just like we did to find the velocities before, where we said that speed is related to kinetic energy. We can use algebra to solve for how far this has compressed, x. I'm not going to make you go through the algebra, but here's what it turns out to be. Just keep this in the margins of your paper somewhere. That extension or compression is the square root of 2 times the elastic potential energy divided by the elastic constant. Very, very similar to speed being the square root of 2 times the kinetic energy over the mass. Same idea. So we're trying to say, how far is this going to compress? We need to know this because we actually still have to design this spring. So this is all theoretical, right? But if I take this to Trimper Rides or someone, they need to say, okay, how long does this really large spring need to be? Because otherwise it won't be able to compress any further, and it'll be like hitting pretty much a brick wall. So x equals the square root of 2 times 170 joules divided by, it's 200 newtons per meter, if you remember, was the K constant. What does that turn into? A lot, Mr. Calculator. 2 times 174 divided by the elastic constant. Not a big number, right? 1.74. Is that the final answer? Absolutely not. Square root that sucker. 1.319, so let's say about 1.32 meters. 1.32 meters. Think about that number. 1.32 meters. The height of my shoulder is about 1.4 meters. This is a pretty long spring. It has to be at least that long, or able to compress that much, I should say, in order for this to work. So you would think about that with your design. So we want to talk about average stopping force. Okay. Let's go back to the work equals force times displacement idea. Get practice with that. Why do I ask all these questions? I'm attacking the same situation from multiple standpoints. Just trying to give you, again, more practice, more experience in these. So average stopping force. If work is force times displacement, then I want to isolate force, divide that displacement over. The force is the work done, in this case on the spring, divided by that maximum displacement. Now this is an average force. That's why I asked average stopping force. Because as you start to compress this spring, the force is 0. Once you get to the end of it, the force is much greater than the average force. So I'll actually graph that out. If this is force versus how far something's stretched or compressed, this would be displacement in our case. You'd have a 0 force and then some maximum. What we're going to find is an average. It's nice and linear if you experiment with it, and it's very easy to find what that maximum stopping force is going to be. So force is work over displacement. How much work was it? Well, let's see. 174 joules of elastic potential energy were stored there. So let's work that out. 174 joules. And the displacement is actually how far it stretched. If I remember correctly, that was 1.34. Oh, 1.32. Okay. 1.32 meters. Now it really just becomes plug and chug. We want to find out what this force was. It's going to be the work divided by that compression. Again, we're just using the definition of work. We're manipulating these concepts so that we can find some unknown. 174 joules worth of work were done on this spring, divided by how far it was compressed, which would be our displacement in this case. The average force to do this is 131, almost 132 newtons. I'll call it force average. Under 32 newtons. All right, that's not something to sniff at in a small situation like this, definitely. It's just a 3-kilogram ball, right? It's like one of those children's bowling balls, or the smaller bowling balls that you would go at an alley with, maybe. So we found the average stopping force. It's actually very easy to find this maximum stopping force because since this is linear, the average is only halfway. So the maximum would be twice that. That's 264 newtons. Sometimes instructors call this smoke and mirrors, going back and forth between things to find some unknown. I call this pulling rabbits out of a hat because you just have to really realize, oh, okay, well, it's a straight line. If I'm halfway up it, then at the end of that line, it's actually only twice the value. So these are just things, it's lab methods, these are problem-solving methods that you have to build up as you go through. But the great thing is you have all these examples which you can always refer back to. Now, if we wanted to look at area beneath the curve, let's say, let me extend this. Let's draw that graph out one more time. So there's our force. It's not a pretty graph, but it'll do. Force in newtons. The compression or displacement in meters. From before, we found that it went from 0 to 264 newtons. So from 0, we'll just stop this here to say 264 newtons. And of course, it's compressed from, technically from 1.32 to a theoretical 0, but we'll graph it out this way. This is actually just a triangle. This is a straight line, or it was meant to be. And if you find the area of that triangle, it's going to also be the amount of work done on the spring, which is the same as the amount of elastic potential energy that's stored in that spring. And it's actually very easy. Area of the triangle is 1/2 base times height. You guys remember that from geometry, or I know if you used to have any of those old agenda books, they always had them in the front. So 1/2 times the base times the height. So 0.5 times 1.32 meters is the base. 264 newtons is that height. Handy dandy calculator once again. 0.5, 1.32, 264, 174 Newton meters or joules. Well, wait, that number looks familiar. 174 joules. 174 joules is the area of this. It's also the work done on the spring. It's also, where is it? Where is it? The elastic potential energy when it's fully compressed. These are all equivalent. So you have some great examples of calculating kinetic energies, gravitational potential energies, even elastic potential energies. You could find the speeds at each point. You have a couple ways to do it now. And don't forget, total energy is boring. Total energy doesn't change. You can always find other energy values as long as you can define what the total energy of that closed system is.